Hey everybody, welcome back to part 2 of health hazards in construction. And as I mentioned in the first part, we will be starting off with silica here in this section. So note that there is a separate silica training that we have for low risk that does go into more detail than what we cover here. This is more of an awareness type level, but should give you enough information to consider whether or not you want to take the more in-depth silica training that we have. So you can just look for that in our library classes, and you should be able to make a determination whether or not you need it. If you have any questions on that, though, feel free to reach out to us at info@lowrisk.com, and we can give you a hand. So we'll get out of the way here, get us down here, and we will move on into silica. So each year, more than 300 people die from silicosis, which that's 300 people. That's quite a few. That's a little less than one per day. Now, if you compare that to car accidents or something like that, it's much smaller number, but it's still a almost, if not 100%, 99.99% preventable workplace disease. So you don't have to die from this in the workplace. So uses of silica are asphalt, cement, or cement, depending on where you're from, ceramics, when we're doing demolition work, jackhammer operations, sandblasting, steel work, stone brick work, rock drilling, welding or cutting, perhaps, depending on what you're working with, and crane operators. All of these people, with welders and crane operators, it's because they're working around construction that has a lot of silica. So maybe demolition operations or cutting concrete or block or brick or what have you. So, but silica is everywhere. It's very tough to go to a construction site and not have some potential for silica to be present. What is it? It's an element, Si. If you remember your periodic table from high school, Si is the symbol. It's a mineral compound. There is crystalline quartz, cristobalite, tridymite. The form depends on where it was created, so pressure and temperature basically. But the thing that we mostly concern ourselves with is crystalline quartz. That is what most people are exposed to when we're talking about silica. So what are the routes of exposure? So if you remember from part 1, we have 4 main routes of exposure. So inhalation, ingestion, absorption, and injection, right? So the route of entry for silica is inhalation. Silica must be released into the air, and then it gets inhaled into the lung. And much like asbestos, the size of silica is fairly small, and it does not dissolve in the body. So it gets down in the air exchange portion of your lung, causes scarring, and then you end up becoming quite sick. And in some cases, it can be fatal. Which I guess going back to that 300 or so number, that's just people that have died. If you've had silica exposure, especially over a long period of time, you can be quite sick for a long period of time and not really get better. You can have respiratory issues that really severely degrade your quality of life, which goes to this first bullet point, that permanent lung damage caused by breathing dust containing extremely fine particles of crystalline silica can cause silicosis. So initially not very many symptoms. Later you start getting difficulty in breathing, you have a persistent cough, and then it progresses into having fever and weight loss and a variety of other systemic or whole body issues. So approximately 3 million workers in the U.S. are exposed to silica dust each year. There was a study in the 1980s that suggested also that silica plays a role in causing cancer in humans. Although these days, what doesn't play a role? But silica, according to some studies, does. So what do we do? How do we keep ourselves safe? OSHA says that we need to measure the amount of silica present. They have what's called an action level, and that is 25 This says 25 micrograms per meter cubed. There's a way to turn this into parts per million, but doesn't matter for these parts. So OSHA says at 25 micrograms, we are at our action level, and then we need to protect workers at 50 milligrams or micrograms, excuse me. And I'll explain what the action and the protection mean. We can also control the dust. So how do we control dust when we're talking silica? Wet method, right, or a HEPA vacuum, or we can provide respirators. So we want to use those wet cutting techniques wherever possible. If you are cutting brick or block, you need to have a saw that has an integrated water delivery system. If you are working inside, you need to have a piece of equipment that has a HEPA vacuum on it. If you are doing really any kind of dry cutting where you can't use water, you need to have the vacuum. Otherwise, you need to have the water, unless you can't do that either. I should mention that with the respirator, and I'm going to go forward one graphic. Yeah. This is wet cutting, but this is not the proper wet cutting. This is the water delivery system here. Though this needs to be operational. At least I think that is the one that's intended to be in this picture. But where I'm going is, if you spray a hose on the block like this, it doesn't stop the silica. There have been studies done where they're able to map the silica, and when you do it this way, you still end up with a lot of silica back behind the saw. It actually needs to be the integrated system there when you use it. So just keep that in mind as you do your work. So how do we prevent being exposed to silica? The best way to do it is prevent the dust from getting in the air. Use wet cutting methods. Next to that, use some type of local exhaust, which would be a vacuum system. You can also use respiratory protection, but that is not intended, according to the new Silica standard, of being the primary method of control. And you, as with many respirators, you can only use them if you have been fit tested and your organization has a respiratory protection program. Now it starts getting into a gray area if we're just talking an N95 mask, like the one that many of us are wearing, or our healthcare professionals wear now in this time of coronavirus. But I'll explain a little bit. We'll look at something called Table 1 in the new Silica standard. And again, we go into this in much more detail in our Silica training. But just know that respiratory protection is not necessarily intended to be the primary protection. Wet cutting and vacuum is. Having chest x-rays and pulmonary function tests are a requirement once you get above that action level, to make sure that you are not being overexposed. Very similar to lead. Lead has an action level as well, at which point, if you're above that, then you are going to need to be tested regularly. Then you also want to use good hygiene work practices. Make sure you are not bringing home or not bringing dirty clothes and other items that contain silica into the home or into your vehicles and things like that. Also washing your hands and just good personal hygiene. So this is a copy of the Table 1 from the relatively new OSHA Silica standard, and it's just a screenshot. And what you'll notice here is it's the equipment / task, and we're going to pick, actually I'll pick this one since it's easy to see. So rig mounted core saw or drill, and then engineering and work practice control methods. So remember, in the hierarchy of controls, this engineering is higher than PPE. So is work practice. This is an administrative control. That's higher than PPE. So what are our engineering or work practice controls for a rig-mounted core saw or drill? Use a tool equipped with integrated water delivery system that supplies water to cutting surface. Well, that's what we said in the previous slides, right? That a wet method is preferable. And operate and maintain tool in accordance with manufacturer's instructions to minimize dust emissions. If you use a water delivery system, you do not need to use a respirator, which what it says here, required respiratory protection and a minimum assigned protection factor. And I'll talk about that APF here in just a moment. But less than 4-hour shift or more than a 4-hour shift, if you're using a wet method, you don't have to use a respirator. It's that simple. Let's see, we'll find one that you do have to use a respirator. So this is dowel drilling rigs for concrete. So that's a pretty specialized operation. But in this instance, the engineering control is use shroud around drill bit with a dust collection system. Dust collector must have a filter with 99% or greater efficiency, that's HEPA, and a filter cleaning mechanism. Use a HEPA filtered vacuum when cleaning holes. And then it goes over here and it says even if you do that, you are required to have a respirator with an assigned protection factor of 10. An N95 respirator has an assigned protection factor of 10. So what they're saying is do this and do this with the respirator. So sorry about that. If you go into table 1 of the Silica standard in construction, the entire table is here with various equipment and tasks listed. Use the engineering controls first and then look and see what is available or what is required whenever you are, what is required as it pertains to respirators. And what you'll find is most of the time you don't need a respirator so long as you do what's on this table. Again, if you have questions, take a peek at our Silica training. It's pretty quick. It's under 30 minutes, and it should give you some more information, additional information that you might need. And then if you still have questions, reach out to us at lowrisk.com. So moving on, I'm going to go to sound or noise. So noise and the subject of sound can get very complicated very quickly. And I've always found when I teach this that it's easy to get bogged down in it. There's a lot of detail. You'd be really surprised the amount of mathematics and other scientific concepts that come into sound. But we'll try to keep it as simple as possible. And at some point, I'm classed out in terms of my knowledge. It gets very complicated very quickly. But there's something called sound pressure. So when people think of sound level, they usually refer to decibels or decibels. Sound is measured by changes in air pressure. So the louder a sound is, the larger the change in air pressure. So right now I'm talking and I'm probably at about 60 decibels or so, 65 decibels. If I start talking louder like this, then there's a larger change of air pressure. So this thing you see here, that's my microphone. There's a larger change of air pressure going against that microphone. So sound pressure is measured in pascals. That is an international unit, an SI unit. But a pascal is very small compared to other pressure units such as pounds per square inch, which is what we're familiar with, like when you fill up your tire or a ball or something like that. A tire pressure of 35 pounds per square inch is equal to about 241,000 pascals. So those pascal numbers are really, really quite large. So we had to come up with something that was easier to use. So that's where the decibels came from. It's from Alexander Graham Bell, so that's why you have Bell. The decibel scale is a very large scale that allows us to measure very large ranges of noise. So every increase of 10 decibels is a doubling of perceived loudness in your ear. So 90 decibels is twice as loud as 80 decibels. Now there's some variables and is it A-weighted and things like that, but we're not gonna worry about that for this class. But know that if you hear it's just 90 decibels, that's twice as loud as 80 decibels because it's logarithmic. So I'm backward shooting this camera, but it goes up in like that very quickly. It's compounded. It's like compound interest. Here are some common decibel levels. So again, like right now, normal conversation, like I said, I'm around 60, probably a little louder. maybe 62, 63. Here's a vacuum cleaner right around 85. You know, a hair dryer, lawnmower, right? Rock concert, I would say rock concert can be way louder than that even. Helicopter if you're up close. Chainsaw, right? iPod or iPhone at peak volume. There's a baby crying, which can be quite loud. A jackhammer, which is really loud. And then our hearing threshold of pain is about 130 decibels. A gunshot is, 130, 140 decibels, and that makes sense. If you've ever shot a rifle if you're shooting the rifle, you don't have hearing protection. As soon as you shoot that rifle or you're near it, your ears ring, and that's because you've had a ton of sound pressure right up against that ear, and really you've probably caused some damage just from that one time. Let's see. We'll go over noise-induced hearing damage or hearing loss. This says noise-induced hearing damage is related to the duration and volume of exposure, which is correct. OSHA limits us to 85 decibels for an 8-hour day, but I'll show you a few more details of that. So this is what our ear looks like. Did you know that your earlobe is actually called a pinna or pinna? Here's your ear canal, right? This is your eardrum. This vibrates, and then it also moves these. There's 3 bones in here that they're calling them ossicles. You've got your eustachian tube, which helps to equalize some of the pressure in your ear. This is your cochlea right here, this nautilus-looking thing, and it all connects to your auditory nerve, which goes to your brain, and this allows you to hear. But what happens is when we have unprotected hearing, we're not protecting our ears, and we have too long noise exposure or too loud at once, this is the cochlea that I showed you. So these are little cilia, like they're almost, you say they're little hairs. And what happens is if you have noise-induced hearing loss, these little hairs get damaged. See the difference? And when that happens, you're not going to get it back. Your hearing is gone to whatever level. So that's why it's really critical that we protect our ears, which that's what I just said. Damage to hair cells starts in high frequencies and moves down into speech, which is about 3,000 to 4,000 hertz. So the frequency of that sound wave is about 3,000 to 4,000 hertz. So what happens is you don't realize you're losing your hearing because it's real high pitched, and then slowly as you get that noise-induced hearing loss, you notice that you can't hear in a restaurant setting, perhaps, or something like that. Other conversations going on, you can't hear as well as you used to, and that's why. So at that point, you've already had some damage done. Now there is normal hearing loss associated with age. It's called presbycusis, but whatever it's called doesn't matter for these purposes. But whenever your hearing is tested, they take that age-related hearing loss into account and they adjust for it. So just know that. So even if you go get an audiogram, get a hearing test, and they say you've had a change over time, they're taking into account the fact that you may be getting older. So the point being, you're losing hearing because you're not protecting your hearing. That's where I'm going with that. So what does OSHA say? OSHA says that the maximum you can be exposed to over an 8-hour day is 90 decibels. So that's 90 decibels over 8 hours. That's a long time to be exposed to 90 decibels. It's quite a bit. Notice that NIOSH, which is the National Institute of Occupational Safety and Health, that's kind of like a research arm, and they do a lot of testing and studying. They say 85. So they are more conservative than OSHA. But basically what OSHA is saying is your permissible noise exposure without attenuating, without reducing without using hearing protection is 90 decibels. If you're at 100 decibels, the max is 2 hours. So, it goes, your max amount of time that you can be exposed goes down very quickly. But I'll tell you, 8 hours at 90 decibels is going to be uncomfortable, probably going to give you a headache, and probably going to cause you some hearing loss. So what OSHA says is if testing indicates that the employee's exposure is above 85, remember there's 85 and there's 90, is above 85, the employer has to develop and implement a monitoring program. So what that says is okay, I went out to your job site, I tested it, and you're over 85, maybe you're 87 decibels on average over 8 hours. You're then going to have to receive a hearing test, an audiometric exam. It's one where you raise your hand or you press the button. And then you are going to be retested in 6 months to see if you've had a threshold shift, basically to see if you've had a change in your hearing. And then you're going to have annual hearing tests every year thereafter. If they have determined that you have had hearing loss, they're going to you should be notified in writing. If you're not wearing hearing protection, you're going to be fitted with the hearing protection. And employees already wearing hearing protection should be refitted and retrained and provided hearing protection with greater attenuation or protection if needed. So only way to prevent hearing loss is to use hearing protection. I would actually go one step before that. You're going to want to consider engineering controls, right? Barriers or moving yourself further away from the equipment. But assuming that's not the case, the only other way is to use hearing protection. There's 2 different types, earplugs and ear muffs. They will have an NRR or a noise reduction rating on them. It's marked on the package. OSHA says you should take whatever that NRR is and subtract 7, basically because they know that we're not going to put earplugs in correctly. So they say if that NRR is 20, you should assume it's really 13. So actually, I'm going to go back to this. So how does that work specifically? Let's say it's 100 decibels where you're working, and your earplugs say that the NRR is 20. It's listed right outside of the package. You're going to subtract 7 from that, so that makes it 13. So if it's 100 decibels where you're working, 100 minus 13, right, is 87. So that means that hearing protection isn't strong enough. You need higher because you want to get it down below 85 decibels. You might have to rewind that to listen to it again, but basically take the NRR, subtract 7, and then whatever that number is, subtract from how loud it is, and you need to get that below 85 decibels. You can double up, let's say in this instance, the NRR from earplugs and earmuffs. It does the work that way. So let's say this one's 20 and this one's 40. You can add those up and subtract 7, and that will give you the protection that you're actually receiving. Just a little bit of information. A combination of 2 different noise sources of equal loudness increases the intensity by 3 decibels. So source A at 80 and source B at 80 decibels together coming to your ears, it's actually 83 decibels. I got ahead of myself. I used 93 here, but in this case, 93 and 93 at the sound to you is actually 96. And then the inverse square law basically means you double the distance. If you double the distance from a sound source, you reduce the noise level by 6 decibels. So if it is at 100 decibels right now, if and I'm 10 feet away, if I go to 20 feet away, then it's 94 decibels. So that's another way that you can especially if you're on the cusp, you can reduce the amount of exposure that you're receiving. So we're going to move on. That is sound. So keep that in mind. Wear your hearing protection. Know what that NRR is. Actually, I'm going to go back. Make sure that you know how to put the earplugs in. You're supposed to reach around with one hand, lift up your ear, roll, if it is a roll type, and then put it in your ear and let go. That's how you put in an earplug. If you don't do it that way, you're not getting the full benefit of the earplug. All right, moving on. A couple of slides. I wanted to touch on radiation. It's not something that many of us, that's not true. We all deal with it on small levels, but not many of us deal with it on very high levels. So essentially, radiation is classified as to whether it's ionizing or non-ionizing. And ionizing is radiation that has enough energy to knock electrons off atoms. That's essentially what it means. Or it can break chemical bonds in molecules. Ionizing radiation is worse because it does exactly what this first bullet point is. It changes the genetic, or the structure, not the genetic, the structure of the atom, which in turn, and actually it can damage genetic material, but in turn that could lead to cancer and things along those lines. It does take a substantial dose, that should say dose, sorry about that, not does, a substantial dose to damage a cell, as there can be trillions of atoms in a single cell. But this image will explain it a little bit better. This disappearing image. Let's see if we can get it up. There we go. Oh, nope. Come back. I apologize. This is live recording, folks. Yeah, if not, that's okay. I'll come back to that. I'll explain it. So there's different types of ionizing radiation: alpha, beta, gamma, X-ray, neutron. So alpha waves, alpha radiation can be stopped by a sheet of paper. That's simple. So if you want to stop alpha, a sheet of paper will do it. Moving up to beta, you need to have thin plates made of wood or aluminum. X-ray would be lead or iron, other thick metal plates. That's why you wear a lead blanket essentially when you go to the dentist, for example, or get an X-ray. Gamma radiation also can be stopped by the same thing. And then you get into neutron radiation. That's where water or concrete, that's what is required to stop it. So that's why nuclear facilities use water and concrete, basically anything that has a lot of hydrogen in it. So how do we control our exposure to radiation? Time, distance, and shielding. Time, distance, and shielding. If we control our time, less time spent near the source, less radiation received. Greater distance from the source, less radiation received. And if we get behind shielding, less radiation received. It's that simple, really, when it comes to radiation. Time limits our exposure, therefore it limits the dose. Distance decreases the intensity and dose. And then shielding disallows us from being exposed to it altogether. So remember that with time, distance, and shielding. Now, if I can't get this to pull up, I'm going to, oh, you doggone it, I'm going to explain it. So let's go back here to, ionizing versus non-ionizing. So examples of non-ionizing radiation would be certain types of visible light. Now there is some ultraviolet, that when you get into ultraviolet radiation, that is actually ionizing. So that's why we have to protect our skin, because UV radiation, ultraviolet radiation, is in that part of the radiation spectrum that is damaging to atoms. So essentially it has the energy to knock electrons off atoms. But if you think of visible light right in the middle, and so this is to my right, I think it's opposite for you, but to my right would be ionizing radiation. So ultraviolet and X-ray and gamma ray and neutron and so on and so forth. That's the bad radiation. That is ionizing, and the wavelengths are very, very small. And they get smaller as you go, so it's just more energy in them. And then if you go the other way, that's where you're talking radio waves and microwaves and so on and so forth. So I know there's a lot of confusion or opinions on this, but that's one reason that cell towers don't cause cancer. It's just a fact. I know, again, some people may disagree with this, but the science is what the science is, in my opinion. But a lot of people are concerned about 5G and things along those lines. But your main concern with non-ionizing radiation is not it causing you to, grow a baby arm out of your forehead or something. The main hazard with non-ionizing radiation is thermal. So if you work in front of maybe some type of communication tower that has microwaves, the danger is that you can basically heat up your body. It is not, however, changing the structure of the atoms in your body. So long story short, non-ionizing, while not dangerous, it is less dangerous than ionizing in terms of long-term effects, unless you stand in front of a source that's going to cause you a lot of thermal problems. So I mentioned that just as an FYI to help you. If you want more information, I encourage you to kind of go take a look, research that. If there's a possibility that you may be exposed to radiation somewhere, remember time, distance, and shielding. If you use one or all of those, it will help you out so that you're not overexposed. So that's it on radiation. I just wanted to touch on it really quick, and we'll get through there. And that is it. That is the end of common health hazards in construction. I just want to remind you, so we covered sound, right? We covered common ways that we encounter hazards, so solids, liquids, gases and vapors, right? Aerosols. We talked about different particle sizes. There's our radiation we just finished talking about. We talked about asbestos, remember? Friable asbestos. We talked about mold. Main key with mold is to control the moisture source and get rid of it entirely if you have had an infestation. And then you can protect your eyes, nose, and mouth if you're particularly susceptible to it. We talked silica, wet cut, or vacuum is your first line of defense, and then depending on the situation, you may use a respirator with an assigned protection factor of 10. So those are our common health hazards. There are others, and I encourage you to identify what those might be. If you have a particularly unique search situation, and that's kind of that's the most powerful part of this is, here at Low Risk we love to train, but our philosophy is that the training that we do here for you is only as valuable as the amount of effort you take into it out into the field and identify things. So my hope is you go out there, and if you hear a loud sound, you'll think about the little hairs laying down in your ear, right? Or if you see someone drilling into a pipe or something, you'll think about asbestos, or you'll think about silica, right? All of those things, that's the hope. But it's up to you to take it the next step, the next level, and help your fellow worker out, protect yourself, and continue to build the culture of your organization. That's it. That's health hazards in construction. Thanks so much. We'll see you on the next one.